Hello, so this is the second half of our lesson on 7.5, which is going to be solving logarithmic equations. The first half of the lesson was all about solving exponential equations, so this would be the back half of the notes. So, just like with the exponential equations, we have different types to look out for, and if we can recognize a certain type of equation, that makes our math a little easier. For this particular type, if you have a single logarithm set equal to another singular logarithm, the only way for this to work would be if their inside stuff is the same. So if you have the same logarithm applied to a value, and then same thing on the other side, that kind of makes logical sense. So whatever's going on here is the 5x minus 1 has to be the same thing as x plus 7. So that's what you're going to set up. You're going to set up 5x minus 1 equals x plus 7, and then you're going to solve. Now we do have to be careful about extraneous solutions popping up when we're solving logarithmic equations. The idea is you cannot take the log of something that is negative. Now that doesn't mean x can't be negative, but that means is when you plug in a number, like for instance right here, if I get an answer of x equals negative 3, negative 3 plus 7 is still a positive value, so that's okay to take the logarithm of. But if I got x equals like negative 20 plus 7 would still be a negative value, and I would have to disregard that solution as an extraneous solution. We'll see that coming up in a little bit, not so much at the beginning of the notes here. So here we're solving. We're going to subtract x and get 4x equals, add the 1, 8, and then x equals 2. Now that doesn't mean, my teacher just told me I don't have to worry about it. We should still check, make sure our answers are going to come up positive inside the logarithm. So 5 times 2 minus 1 is 9, so that's good. And then 2 plus 7 is also 9. So good. All right, here. What I'm going to do in this next couple examples is I'm going to show you why this is true. When we are solving a logarithmic equation, the way you undo a logarithm is you create an exponential equation. So what we're going to do is called exponentiate. And you can technically shove numbers underneath equations, as long as you do it to both sides, and then hoist the equation up into the exponent position. So since I can do that, I'm going to choose a base that makes sense for me. If I have a natural logarithm, what I'm going to do is I'm going to choose the base of e, and I'm going to shove it underneath the equation, both sides of the equation. So what you technically have right now is e raised to the natural log power of 6x plus 3 equals e raised to the natural log power of 2x plus 27. So think back to your inverse properties. E raised to a natural log power. The e and the natural log have the same base, and they are inverses of each other, and what that does is it cancels them out, and then the 6x plus 3 drops down. And then same thing over here. Cancels out, and the 2x plus 27 drops down. So that's why this, if this equals x equals y, occurs. Clearly, I don't want to have to go through the exponentiation work if I don't have to. So I'm just going to solve this. I'm going to subtract 2x from both sides. We get 4x. Let's go ahead and subtract 3 while we're at it. 4x equals 24, and x equals 6. And then again, even though my teacher told me I'm not going to have to worry about it, we should always check for extraneous solutions. So if I were to plug in a 6 right here, that's a positive number. Let's see, it would be 39. And then plugging in a 6 here, that's also 39. So it checks out. All right, here, log base 8 of x squared equals log base 8 of 16. So you could exponentiate both sides with an 8. But we know what's going to happen. This 8 to the log base 8, they're going to cancel. So you end up with x squared equals 16. And then when you square root both sides, we do have a positive and negative 4. So we have two different solutions. And I know we talked about maybe crossing out negative solutions. It's not that they're negative solutions. It's that when you plug them into the logarithm algebra, they can't be negative. So think about what's happening here. You're squaring whatever the x is. So if you took negative 4 and squared it, you're still going to get a positive 16. So we get to keep both solutions, positive and negative 4. So those would be the simplest logarithm equations, but it turns out they're not always that simple. For instance, here, you don't have logarithms on both sides, so you don't have that one-to-one property. But the idea of exponentiating is definitely something we're going to use here. So you can choose to exponentiate your equation on both sides, as long as you use that base on both sides. So when I look at this question, we have log base 5 equals 2. So to undo or get rid of the log base 5, I'm going to exponentiate with a 5, but rule of math, if you do something to the left side of the equation, you have to do it over here on the right side as well. So this is what you have. You have 5 to the log base 5 of 3x plus 1, all that's in the exponent, equals 5 to the second power now. So this side, yeah, those cancel. 5 to the log base 5, and the 3x plus 1 is just going to drop down. But 5 squared, nothing cancels there, but I can't simplify it. 5 squared is a 25. And look at that, ladies and gentlemen, we have a two-step equation to solve. Let's subtract the 1. 3x equals 24, and x equals 8. And again, I have to watch out for extraneous solutions. And it does say round to the nearest thousands. That's only if you have to, like whole numbers, integers, we don't need to round. Plugging in an 8 right here, 3 times 8 plus 1, that would be 25. So we're good. We don't have to do any rounding. And we also don't have to worry about crossing off for extraneous solutions. So gut instincts here, I'm going to ask kids in class, what do you think you should do first? And most of them are going to come back with, we should isolate the logarithm. So let's divide by 12. So right now we have the natural log of x equals something. 44 over 12 is 3.6 repeating. So I'm going to write that as a fraction. I'm going to write it as 11/3 for now, just so I don't have to do any rounding. And remember, we're going to exponentiate with whatever the base is. Well, natural log is a log base e. So we're going to exponentiate with a base e on both sides. So for your notes, I would like you to write down what you're really doing, because I think this is hard for kids to understand. You're shoving an e underneath the problem and creating exponents. It's a thing. You can do it. So here, e to the natural log of x, the e and the natural log will cancel because of the inverse property, and the x will just drop down. And then e to the 11/3, make sure that you're using the caret to bring the 11/3 up to the exponent. So e to the 11/3, remember e is the second natural log button. That's the best way to use it. Please practice typing this. You should get 39.121 when you round to the thousandths place. A lot of kids do e times 11/3, which is not exponentiating, and that's why they keep getting it wrong. These are also the same kids who ignore me when I tell them to practice typing, so don't be one of those kids. Alright, the natural logarithm is isolated, so now we're going to exponentiate on both sides. So e, and then this is now raised up. Same thing over here. That's great. These cancel, so the 3x minus 2 will drop down, but you still have e to the 2.8 power, which is something funky on my calculator. So I'm going to add the 2 over. So I'm going to type this in, e to the 2.8 power, and then get out of the exponent before you add 2, or hit enter first. So that is 18 point something. So 3x equals 18.445 when you round. And then when you divide that by 3, you get 6.148 roughly. Again, truncation and rounding sometimes creates a little bit of an issue with the last decimal point digit, so don't panic if you're one thousandth off. Alright, please practice typing that. Alright, this next one, the log is isolated, so now we get to undo the logarithm by exponentiating. It is a base 4, so we're going to use a 4. So shoving a 4 underneath both sides of the equation. This is awesome, because 4 to the log base 4 will cancel, and then the 5x minus 6 drops down. And then 4 to the 3rd power, remember we're going to type that like this, or use our chart, or use our brain, that is 64. And then adding 6 to both sides, 5x equals 60, and x equals 12. Lovely, huh? Alright. Not too bad, not too bad. Let's see what else they got. Oh boy. So we can't exponentiate until the logarithm is isolated, and frankly, you can't have more than one logarithm on one side. This is just not something we can handle. So I need to think back to our previous lesson, 7.4, and think if there's a way that I could condense or rewrite this as a singular logarithm. And by the way, this is a common log, so it's log base 10. If you want to write a 10 here, you sure can. So we got to think about, how do we condense logarithms? Well, we take the inside stuff, and if it's log plus log, the condensing formula says to multiply those together. So you have a 5x times an x minus 1. Ooh, I think this is the question that's really bad. Okay, anyways, we'll get to that in a second. Equals 2. So, exponentiating now, because I do have a singular logarithm, exponentiating with a 10 underneath both sides of the equation. These are gone, and you get 5x times x minus 1 equals 10 to the 2nd power, which is 100. Oh no. Alright, so you have 5x squared minus 5x equals 100. Ladies and gentlemen, we have a quadratic. Alright, so we have 5x squared minus 5x. minus 100 equals 0. I'm going to do everything I can to help myself here. So everything here is divisible by 5, right? So this becomes x squared minus x minus 20. Oh, this isn't too bad. This one factors. Think about how we could factor. Multiplies to negative 20, adds up to negative 1. That would be x minus 5 times x plus 4. Sorry about that. That little visitor. That was a 4. So my factors are x minus 5 times x plus 4. And if I solve each of these, I get x equals 5 and x equals negative 4. Now, remember, we should always check for extraneous solutions. If I plug in a 5 inside this logarithm, I have log 25. Totally fine. And then plugging in a 5 here, I got log 4. Fine. But if I plug in a negative 4, 5 times negative 4 is negative 20. And log applied to a negative 20 does not exist. It is not defined. So this is an extraneous solution. Not going to work. X equals 5 is our only solution. So that's why there's a little note here to check. That's what it looks like when it's extraneous. When you plug it into the logarithm, either one of the logarithms, it can't give you a negative value that you're applying the logarithm to, because that is not defined. I mean, think about what a logarithm looks like. Like this, right? It doesn't go negative beyond the asymptote. So as far as x values, it's not defined along that domain, I should say. All right, this next one, this is the awful problem. Because it's base e, we would be exponentiating with an e, and then we'd have to do quadratic formula with an e. And I just don't want to do that. So I'm gonna skip this question. I think that's the end of our lesson. Oh no, it's not. This is a good one. We're gonna skip 14. I like 15 though. Too many logarithms. I can't handle it when it's written like this. And you know what? For the sake of fun, can we change this question to a subtraction sign right here? And can you tell me, think back, how do we condense log minus log? Well, that becomes a division problem. That's the quotient condensing problem. So we have log, which is a base 10 because it's common log. And then this becomes x minus 6 over 2x minus 11. So I changed the problem to say log minus log, just so we're clear. And then equals 1. So now I can exponentiate with that 10. And I end up with, these cancel, gone. So I just have x minus 6 over 2x minus 11 equals 10. Boys and girls, that's a proportion. So let's cross multiply here. 10 times 2x minus 11 equals x minus 6 times 1. And then this isn't too bad to solve. It's just a linear equation. So we have 20x minus 110 equals x minus 6. Lovely equation as always. Very good. Subtracting x from both sides. Let's go ahead and add the 110 while we're at it. Gosh, I can't write. So you get 19x equals 104. And then, I don't know if that divides. Since my brain isn't, no. Alright, so 104 over 19. So, x equals 104 over 19, which, P.S., is approximately 5.47. Now, remember, we should check. So if I were to plug in a 5.47, boom, right there. And then I subtract 6. That's going to give me a negative value inside of that logarithm. So this is actually no good. It's extraneous. And since that's the only solution I got, and it doesn't work, there is no solution to that equation. So bang up job, Abruzzo. Not only did you have to change the problem, you made it no solution. It's okay. That happens sometimes. All right, that, I think, is the end of our lesson. So first half of the lesson was solving exponentials. Second half is solving logarithms. There's separate skills in our gradebook. There's separate skills in life. They're similar in respect to the fact that they're inverse functions, but the approach is very, very different. So keep them straight in your brain and make sure that we are doing mathematically sound things. We're exponentiating logarithms, and we're applying logarithms to exponents. Good luck.